All right, this is note card 8. It's titled The Average Rate of Change. So it says the average rate of change of a function over an interval is called a difference quotient. And the way we find it, so we take the amount of change, or the delta y, over the length of the interval, which is the delta x. So this is the formula for the average rate of change. And sometimes we abbreviate that as AROC. Okay. And it's also the slope of the secant line through 2 points, and also gives us two other equations. Now we'll get to these eventually. Okay, we'll actually get to these in another lesson. So let me give you a graphical view. Now, when we think about average rate of change, what I think of as average rate of change is simply the slope of a line between 2 points. Because it's got that same type of formula, delta y over delta x, and we think of that usually as the slope. We abbreviate with the letter m. So let's say I just draw a graph. And on the y-axis, we'll say distance from home, measured in miles. And on this axis, we'll say time, measured in hours. Okay? And whether you're on a bicycle or you're in a car, it doesn't really matter. Or you could be running or walking. Let's just say we have this type of function real quick. If we want to find, let's say we start, and that's 0, we start at 0, time 0, and we end at time, I don't know, 7 hours. Okay, so let's say we start maybe at someone else's house 5 miles away from our home. Okay. And at 7 hours, we might be at, let's say we're at 425 miles, 425 miles away. If we could take a line and connect the starting and ending points along this journey, the slope of this line, well, first off, this is called a secant line. Now don't confuse the word secant with the trig function secant. A secant line is just a line between 2 points. And if I were to look at the slope of this line, that's going to equal the average rate of change over the time interval 0 to 7 hours. So how would we actually find that slope? Well, a slope is just a rise over a run. Okay, so we're going up from 5 to 425. So we're rising 420. Okay, and we're rising 420 miles, and we're running 7 hours. Okay, so if we do delta y over delta x, that's like saying rise over run. We went up 420 miles, and we rose 420 miles, and we ran 7 hours. Okay, and you can actually simplify that. 42 divided by 7 is 6. Okay, so 420 over 7 would be 60. And what would the units be? Miles over hours. The abbreviation for that is miles per hour. Okay, so our average rate of change would also be the average speed. We would be averaging 60 miles per hour. Now there's another way to do that. We kind of talked about this in note card 1. Another formula on here says f of b minus f of a over b minus a. So think about the b as 7, think about the a as 0. Okay. So here this would be like f of 7 minus f of 0 all over 7 minus 0. Well, what's f of 7? At 7 hours, my position is 425. Minus, what's f of 0? What's my position at time 0? It's 5. And both of those are measured in miles. Over 7 minus 0. And if you simplify, you get 420 over 7, and you still get 60. And those would be the units. Miles per hour, or abbreviated MPH. And that's your average rate of change. Okay, the secant line connects those 2 points, and all you're doing is finding the slope of that secant line. That is the average rate of change. Okay, so what we did here, we just found the average rate of change between 0 and 7. So now let's look at some of the questions. It says, in an experiment of population of bacteria, find the average rate of change from point P to point Q and draw in the secant line. Okay. Well, here's P and here's Q. So if I'm going to draw in the secant line, I'm just going to draw on a line connecting those 2 points. Okay. All right. So how would we find the slope there? Or basically what I'm trying to do is find the average rate of change from P to Q. So we would do delta y over delta x. How much do you have to rise? How much do you have to run? Well, how much do you have to rise? You're going from a y value of 150, that's right there, to a y value of 340. So you're going up that amount. Okay, so a quick way to find that is just take 340 minus 150. And what's your change in x? How much are you running? Well, you're going from 23 to 45. So a quick way to find that is just 45 minus 23. You can see here that this secant line has a positive slope, so my answer better be positive. All right? So before we actually simplify this, let's think about units. What are the units of these are both y values. My y is the bacteria per, what are the units of 45 and 23? These things right here, those are days. Okay, so if we do some simplification here, 340 minus 150 is 190. 45 minus 23 is 22. And then we can turn this into a decimal if we want. So in a calculator, just do 190 divided by 22, and you'll get 8.636. The units would be bacteria per day. Okay. Or if you wanted to do this in one step in your calculator, just set up a fraction, 340 minus 150 over 45 minus 23. It gives it to you as a simplified fraction. If you hit the math button, you can convert that to a decimal. Oops. Same thing, 8.636. Okay. So what's the meaning of this? Okay, here's the meaning. Between the 23rd and 45th day, the population of bacteria is growing because that number is positive. It would be, if it was negative, it means it would be declining. So the population of bacteria is growing at an average rate of 8.636 bacteria per day. That's the meaning of it. So let's do number 2. So this is a form of free response question where you were allowed to use your calculator. Traffic flow, F of t, is defined as the rate at which cars pass through an intersection, measured in cars per minute, and t is in minutes. Okay, so if I'm going to just start to make a sketch of this graph, this F of t would go on this axis, okay, and that's measured in cars per minute. And this axis, the time axis, it's measured in minutes. All right, the traffic flow in an intersection is modeled by this function. So they give me an equation of a function, and that function's good over this time interval. What is the average rate of change of the traffic flow over the time interval between 10 and 15 minutes, and indicate units of measure? So I want to find the average rate of change over the time interval 10 to 15. Let's go ahead and graph it. So I'm just going to go into y equals, okay, and I'm going to type in this function. Now make sure you are in radian mode, because everything in calculus is radians in terms of trig. So 82 plus 4 sine t over 2, so we'll set up a fraction, but I can't use t, I have to use x instead. So the x-axis is like the time. Okay. And that's good. Before I hit graph, I'm just going to put in this time interval they gave me. So I'm going to say between 0 and 30, we can step by 1, or scale by 1, and then I'm going to do zoom, and I'm going to go down to zoom fit. I'm going to hit enter. So here's what the curve looks like. Okay, it's some sort of sinusoid function. No big deal. Okay. And then I can hit window again. Maybe I want to start just realize that my y-min, the calculator is set to 78. So when I look at this graph, it's a low point of 78. It doesn't start at 0. The y values start at 78 and it goes up to 85. Okay. So what we want to do is we want to, if you actually fix this window, if you change your y-min to 0, it's a more realistic graph, starting at 0, 0 instead of 0, 78. Okay. So it kind of does one of these. Okay, does one of these. And what we want to do is we want to now focus in on between 10 and 15. So 10 might be somewhere around there, 15 might be somewhere around there. And what we want to do is we want to find the slope of the line between there. So how would we find the slope in between there? Okay, well, we would take this is the delta y, that's the change in y, how much you rise. Okay, so it's delta y over delta x. That's going to be the same thing as this y value, which we can call f of 15, minus that y value, which we can call f of 10, over these numbers themselves, the change in x. So the change in x, I'm going from 10 to 15, so I just do 15 minus 10. And the units of the y is cars per minute, and the units of x is minutes. So let's go ahead and now look at it just from 10 to 15. So I'm going to go into my window and I'm going to just fix it to 10 to 15. So it does look like if I drew in a secant line between those 2 points, it would be slightly increasing. There's a quick way to do this in the calculator. I'm going to set up a fraction. I'm going to say, okay, calculator, I want you to tell me the y value at 15. So I'm going to use my shortcuts. I'm going to hit alpha, and then I'm going to hit trace. I'm going to choose option 1 because my function is in y1. So I'm going to say, calculator, tell me the y value, or the y1 value at 15. Subtract off the y value at 10. Then in the denominator, I just do 15 minus 10. Hit enter, and there we go. 1.518 if I round. So my answer, 1.518. So that one, the question probably seemed harder than it was. That's all you have to do. You're finding the slope of this secant line between those 2 points. Now, problem 3. It says, use the table below where f of t is population, so people, and t is a time. Okay, so population is measured in millions of people, okay, and time is measured in years. It says, estimate f prime of 1870. Now, you haven't seen this notation yet. What's f prime? That's a slope of a tangent line. That's a slope of a tangent line. So what is a tangent line? Well, here's what a tangent line would be. Okay. If you had some curve, and I don't really care what the curve looks like. All right. If you look at a specific point on that graph, a tangent line comes in and just hits that single point right there. It's different, so this is a tangent line. It comes in and touches that one point, as opposed to a secant line, which connects 2 points. Okay, so here's the thing. If you look at the slope of this tangent line, and you look at the slope of the secant line, the lines are pretty close to parallel, so they would have the same slopes. As long as you choose 2 points really close to this point, the slopes will be about the same. All right, so looking at your data here, if this was the year 1870, if I picked 2 points instead close to 1870, maybe like 1860 and 1880, and I measured their slope between these 2 points, it would be really close to that slope. It would be really close to the red line slope. Okay. So here's how I'm going to write it. Here's how I'm going to take that and apply it. Okay. So I'm going to say f prime of 1870 is approximately equal to, okay, this would mean slope of tangent line at 1870. It's approximately going to be equal to the average rate of change between 1860 and 1880. Okay. Now, why did I choose 1860 and 1880? Because those are the two closest numbers to the 1870. All right, so how would I figure that out with the formula? That would be F of 1880 minus F of 1860 divided by 1880 minus 1860. Now, where am I going to get those values? What's F of 1880? What was the population in 1880? It was 50.2 million people minus the population at 1860, which was 31.4 million people. And if I subtract these two numbers from each other, 1880 minus 1860, that would be 20. And if I go ahead and put that into the calculator, 50.2 minus 31.4, that's 18.8. If I divide that by 20, I get 0.94. Now think about units. The numerator here, the numerator is measured in millions of people per year. So what's the interpretation of this? 0.94 million people. Well, if that was just 1.0, that would mean 1 million people. So this actually represents 940,000 people per year. Okay. So there's the answer. That's an approximation for part A. Now interpret the meaning. Okay. In the year 1870, the population, think about this, this number is positive, which means it's growing. The slope between these 2 points gave me a positive value. 0.94 is a positive value. So in the year 1870, the population is growing at a rate of approximately 940,000 people per year. Okay. So in that year, that's how the population was growing. Okay. Or you could say the average rate of change between the years 1860 and 1880. During that 20-year span, the average rate of change, or the average growth of the population, was 940,000 people per year. So this note card illustrates this important concept where average rate of change is the slope of the secant line, which can approximate the slope of the tangent line. Okay, and the tangent line slope is also called the instantaneous rate of change. Okay. How quickly is something changing at a specific time? Well, we need calculus to figure this out, but eventually we will learn how to find this. But the secant line slope is referred to as the average rate of change, or AROC. So that's called AROC. This one, shorthand, is called IROC. Okay. There is no UROC. It's only AROC and IROC. So average rate of change, slope of the secant line, instantaneous rate of change, slope of the tangent line. This has another name. It's called a derivative, and we'll get to that. So there is no packet associated with this note card. So hope you found the information useful.